So at any rate, we'll just go right forward. If you've ever had the privilege of driving across south of Chicago where 80 and 90 run together, you probably remember a traffic jam with toll booths. But as you can see up here behind me in this beautiful digital elevation model from Tom Lowell, not only is it a traffic jam with toll booths, but it's actually the footprint of a long gone ice sheet. And the ice came out 24,000 years ago and put down ridges, and then it sort of sawed back and forth, and it left this beautiful landscape that we have adorned with toll booths. But those of us who study the history of climate, whether it be in Illinois or whether it be in Greenland, as you see here, have a prettier landscape than the rest of the world does. And so I want to walk you through a little bit of our studies of the history of climate. So those of us who do history of climate, paleoclimatology, are dedicated to trying to find out what happened, when it happened, and why it happened. You will meet people who say, you're just telling stories, and no, we aren't. We actually will generate hypotheses that lead to new measurements, that lead to new samples that are taken specifically for hypothesis testing. And fascinating, people say, oh, look, there's a change in the North Atlantic that predicts the protactinium-thorium ratio of the sediments, and you go measure it and see if it does. And so it's a fascinating field. It's a very fun field that we work on. And we have to work a lot on finding histories and how do you relate climate to something we can measure. So you saw the footprints of the ice sheet. That's a piece of cake. Some of the indicators we use, we went to Greenland, we drilled through the ice sheet. A mile down in Greenland is colder than the top, and it is colder than the bottom because it has not finished warming up from the ice age. And how cold that is, it takes a long time to heat the middle of a turkey in an oven. It takes a really long time to heat a 2-mile ice sheet. And how cold that is tells us how cold the ice age was. We have this amazing range of indicators across physics, chemistry, biology, isotopes, and more that actually do give us a picture of how the world changed with a great amount of confidence, to be honest. I'm going to walk you through this history. The recent stuff is just pound on the table near certainty. The older stuff is a little fuzzier, but I'm going to try to pull out the key pieces, and I'm going to do it to highlight one question, which is the role of CO2 in this at the end. This is not where we started. When I was a student, we didn't think CO2 was that important in all of history, and what we've learned is that it is. And so I'll walk you through where this came from. If you ask what can change Earth's climate, all kinds of things can matter. And I'll walk you very briefly through them. How much energy we get from the sun, how much of it gets blocked on the way, how far it comes, how much of it gets reflected, how much of it stays in the Earth system. That's the whole thing, right? There's Earth's climate in a nutshell. And so we'll walk you through. Fascinating thing. When the sun changes fast, the climate immediately knows. When the sun changes slow, the climate beats it. And I'll show you this stabilizer. It's a fascinating thing. And we're fortunate that when the sun changes fast, it doesn't go very far. If the sun was really highly variable, we would be in deep doo-doo, but we are not. And so you can do things like this. So if we make it click somewhere. So this plot is showing 1,000 years ago is over here on your left. Today is over here on your right. Temperature history is sort of the center of this gray band running along here. And up here are changes in the sun and changes in volcanoes blocking the sun. Edward Bard, new member, is working on improving some of the changes in the sun pieces, but it's not going to change too much for that. And if you take climate models, lots of them, and you tell those climate models what the sun did and what the volcanoes did to block the sun, you will notice that all these different climate models actually agree with what really happened pretty well. Until you get really recently over here on the right, whereas if you don't tell the models about humans, nature has been trying to cool it off when in fact it warmed up. The sun changes, the climate changes. We are fortunate the sun changes are small over our timescales. And volcanoes, if they could get organized, would rule the world. But there's no way for a volcano in Indonesia to tell a volcano in Alaska that it's time to erupt. And so they're noisemakers. Okay? Now, if you ever worry about changing distance to the sun, at some point I asked Jim Casting, I said, Jim, that meteorite killed the dinosaurs. How far did it move the Earth? And he said, about that far. Don't worry about this one. Okay? Right? And we can ask, does the blocking of what comes from the sun change very much? And yes, the meteorite killed the dinosaurs. It changed the climate by blocking the sun, by blasting stuff around the Earth. But other than that, it's really, really hard to find much of a signal of things coming from space making a difference. And so we can measure tracers which are ultimately linked to coming from space, and these numbers are pathetically tiny, and they don't change very much. So really, aside from this one crazy rock and a bunch of rocks way back in time that blasted, the moon did not spin out of the Pacific, retract that one, as Walter Munk would say, but the moon did come out of a collision with high confidence, but that's way back. And for the times that we care about, is space dust mattering? It doesn't look like it. And you can measure that, you can say that with confidence, okay? You change how much reflects from the Earth, and that matters. And there's no question about that. And sea level is, ocean's a little darker than land, sea level changes, there's a feedback on that. But it's pretty hard to find a knob that changes albedo all by itself. It's something else changes that changes the clouds, that change the ice and other things. And in particular, you'll find people have worked very, very, very hard to see if there's any chance that cosmic rays matter. And the cosmic rays zap into the Earth and they ionize the atmosphere, and that affects cloud condensation nuclei, and that affects clouds. And what you see behind me here is an ice core record. Today is on your right. We run time either way. I'll keep changing it because we do. Today is on your right in this one. 60,000 years ago is on your left. Right here, about 40,000 years ago, the magnetic field went essentially to zero. And we see that in magnetization of lava flows and sediments. And when that happened, cosmic rays came streaming into the Earth system. They broke molecules and made beryllium-10 and radiocarbon and other things. And the beryllium-10 fell on the ice sheet. And so you can see this big spike here, which is cosmic rays. And you'll notice that the climate record ignored it. Now, this does not prove that cosmic rays are zero, but the climate record ignored it. Not a big deal. And so we actually get to this sort of fascinating thing that walking through what can change the climate, we come down to the greenhouse effect fairly quickly as a big deal. And now this will be a big deal, as I'm going to show you that. So how do we find out how strong the greenhouse effect was? For the last 800,000 years, we have ice core bubbles. The different ice cores, different chemistry, different snowfall, different temperature, different impurities, the same record. The overlap with the instrumental record is beautiful. This is the gold standard. We can do methane, we can do CO2, other sorts of things. Older than the ice cores. You know, ice is not forever. Older than the ice cores, it takes a little more cleverness. And I wish I had time to tell you just how much cleverness is in here. So Kate Freeman's work and Turi Serling's work on carbon isotopes, work on stomatal density. Plants grow fewer water-losing stoma when they have more CO2. Work on boron isotopes and boron concentrations. And there's a remarkable agreement appearing. 10 years ago, these indicators didn't always agree. More and more they do in reconstructing histories of CO2. Okay? So we'll start you off with the deep fuzzy ones, and then we'll come towards the present nailed ones. You probably know this problem. Carl Sagan identified it. The sun burns hydrogen to helium, it packs more mass into a smaller space, that pulls the sun in stronger, that burns faster, the sun's getting brighter. We don't have a record of that. There's nothing that the sun says 70% of modern at 4 billion years, but the physics is so clean that there's really no way out of this. And yet the geologic record looks like today, liquid water dominating the Earth, very little evidence of ice at most times, with a sun that was dim enough that we should have been frozen. And so there's this question, how did we have so much stability of climate for so long in conditions with liquid water when the sun was dimmer? And you can't do it with albedo. You'd have to make the Earth perfectly black to solve this problem. The Earth would never be perfectly black. It has to be the greenhouse effect. Okay, now, when you ask what controls the greenhouse effect, it almost certainly is several gases. It is not just CO2, but CO2 is in there. And so here's your diagram from class. I was teaching this last week, and stuff comes out of volcanoes, and it does chemistry, and it goes back down subduction zones to come out, and that's too complicated for class last week, so let's make it really simple. Okay, stuff comes out of volcanoes. What comes out of volcanoes? Rock and CO2 gas. And this makes it warmer, and this sits there. And how fast it comes out of volcanoes doesn't care much about the climate. It cares about stuff way down there. But then what happens is what came out of a volcano, CO2 and rock, can react into dissolved things that get turned into shell or the inorganic equivalent of shell that goes down the subduction zones. And this is chemistry. And those of you who are chemists know that there are Bunsen burners in the lab for a reason. And in point of fact, when it's warmer at the surface, this takes CO2 out of the air and turns it into rock. And this is a very, very powerful stabilizer. If it gets hot, this takes CO2 down. If it gets cold, this leaves CO2 up. The CO2 warms, and so on. And so this is a very powerful state. It's a slow stabilizer. It takes 500,000 years. We put up a lot of CO2 in 500,000 years. This will take care of it. If you've got 500,000 years to wait, no worry. Okay? So, but there's an interesting thing. Anyone who is interested in sports knows that if you have a very strong, very slow defense, that you might beat it with a fast break. And so if the Earth is stabilizing its climate long term with a very strong, very slow stabilizer, you might think there would have been times that it got beat. And so we'll find one of these that clicks forward. There we go. So in fact, we do think there were times that it got beat. And that's these times. So these are maps. They have times up in the corner here. These are certain special times when this general lack of ice seems to have gone away. And the continents were where you see them. And the stars are evidence of glaciers. And what you will notice is that certain of these times in the past, these stars are at the equator and they're sort of all over everything. There are these certain special times that the Earth seems to have turned into a snowball. That might be consistent with our idea of a big, slow, powerful defense. Now, if you make a snowball, you cover the Earth in ice. It is very reflective. It takes a long time to build up enough volcanic CO2 to make it warm again. And then that volcanic CO2 should make it really warm. You should see an immense amount of rock weathering taking CO2 down, and you should see an immense amount of inorganic equivalents of shells. So there's a prediction here, which is that if this CO2 mechanism is working, the end of a snowball should see huge amounts of CO2 turning to rock after making it warm and melting the snowball. So what do? I've got, so there's the story in words that I just told you. And here's the picture that doesn't. Right? And there's lots of these. This is Paul Hoffman's picture. These are the deposits from the glaciers down here. And these are the rocks containing CO2. It's a magnesium-calcium one, but this will do. And if you write the rock as CaCO3, which is sort of the old way, the new way to do it, you may not see the CO2, but if I write it CaO.CO2, you see it. And there it is. CO2 is a big deal in a lot of Earth's history. Okay? Now, this is a thermostat. It is a powerful thermostat. It brings the temperature back to a set point. Anyone who has roomed with someone or been married to someone with a thermostat knows not only that the thermostat brings the temperature back, but you may like a different setting than your significant other does. Okay? It may not surprise you that the Earth will change the setting of the thermostat by things like, are there mountains with soil falling off that make it easier for the CO2 to get to the rocks? Evolution, plate tectonics over 100 million year time scales will change the thermostat. And we expect this. There's really no way to avoid it. And so what you get is something like this. So this figure is from the IPCC. We have now time. Today is on your right at the moment. 400 million years ago is on your left. These are various records of CO2, all sorts of different independent ways to do CO2. And above is where there was ice on the planet, coming towards the equator. And what you'll notice is high CO2, no ice, low CO2 ice, high CO2, no ice, low CO2 ice. And because of our understanding of these stabilizers, it is not the case that warmth made CO2 high. It is the case that CO2 made warmth, because our understanding of the physics and chemistry of the system gives you the direction of the arrow. This actually works pretty well. And so in point of fact, what you see is the thermostat being reset and the climate history looking like the CO2 history. Right now, this is a beautiful view. I'm sure some of you have seen this view. And a geologist, of course, sees this view and also sees lines drawn across it. All right? 200 years ago, the geologists started naming things. They said, wow, something died here, and then new things appeared, and we'll change the name. This is a Paleozoic, and this is a Mesozoic. This is a Mesozoic, and this is a Cenozoic. They didn't know why the things died. For some of these lines, we still don't know. But one of the lines is a meteorite that killed the dinosaurs, and the other lines for which we now know look like climate changes. And several of them have CO2 as the driver of the climate change. And so you go back in this history, and here's one. This is the Pliocene-Eocene thermal maximum. And what you see coming, this is now a core record. And 56 million years ago is the bottom, 54 million years is the top. And here's CO2. This CO2 came from formerly living things. It's isotopically light. And temperature increases to your left, and what you'll notice is CO2 came out and the temperature went up. And then all kinds of, a few things died, a lot of things migrated, big things became dwarfed, the soils changed, the plants changed, who was eating the plants changed, everything on the planet pretty much changed because CO2 came out and it got warmer. This was formerly living CO2. This one, I don't have a plot up, but this one, the biggest extinction, happens to come at the same time as the biggest outpouring of volcanic lavas. Huge amounts of CO2, some weatherable rocks, a little sulfur. The ocean gets hot, it loses some oxygen, it gets full of hydrogen sulfide that comes out and poisons things. The ocean gets very acidic. It probably gets too hot for large creatures to live near the equator, in the ocean or on land. And most of the things on the planet died. And it's inorganic CO2 with the stuff that came with it out of the volcanoes. Okay. Now, we'll walk over a bunch of others real fast. If we had a whole class, we'd do these. But at any rate, we're going to come up to the ice ages recently. The ice ages recently are not caused by CO2. But, right? Okay, so here's a climate record from Antarctica. 400,000 years ago. It's not 400 million, 400,000 is now over on your right. Today is over on your left. Temperature is in blue, and I hope it's completely evident that this does not look like a random number generator made this curve. Okay? And you can see the sort of tick, tick, tick of 100,000 years running across here, and some other ones that are faster. There's a 41,000 year one in there, and I'll do this for you very briefly. North Pole does not stick straight up. It's tipped over a little. It tips a little more and a little less. That's 41,000 years. And if I do a fast Fourier transform of that plot, what I find is a lot of variability at 100,000 years. There's the 41,000, and there's 19 and 23. These were predicted 50 years before they were observed. Milankovitch says these things move sunshine around on the planet. When you people finally get a good record and date it well, you will discover under my arrows, you'll have peaks. 50 years later, what do you see? Under the arrows are peaks. This is not caused by CO2, it's caused by orbits. But there's this funny thing. All that does is move sunshine around, tiny tiny little bit from eccentricity on total amount, but it's basically this melts ice at the pole and less sun at the equator, and then more at the equator and less at the pole. And Milankovitch said either the ice ages will go north to south, or they'll go equator to pole, equator. Okay. But what actually happens is the whole world changes together. And you get this kind of crazy stuff going on. So here, today is over on your left now. And what you'll see here is today is right here, and older is back here, and here's CO2 in the air. And this is sunshine at South Pole, and this is temperature right next to it. And what you will notice here is that midsummer sunshine is high when it was cold, and midsummer sunshine is low when it was warm. There is a signature of southern sunshine and southern temperature, but southern temperature also looks like Canada's sunshine. Because the whole world changes together, even though the sunshine is doing seesaws. And when you ask, why is that? The only successful explanations that have ever been generated are this red curve above it. And if you include the fact that all kinds of things change during an ice age, you grow enough ice on Canada that you lower sea level by 100 meters, you change currents, you change wind, you change fertilizer to the ocean, you change a whole bunch of things. Some of those bring CO2 out, some of them put CO2 in. The net is, when ice grows on Canada, CO2 drops, and that globalizes the signal. And half of the world ignored its own sunshine because the CO2 was more powerful than the sunshine in controlling its temperature. And now, just for the scaling, right, I have rescaled the plot. Today is on your left. We are right there on CO2, and we're headed off the plot. So this is what, now remember it's a log scale, I didn't do log, but so I'm cheating a little bit here. But this is what globalized the signal, and there's where we're headed. Right? So where does it leave us? Right? Earth's climate is almost everything. And it really does care about almost everything. And be honest, it's, if you move the continent from the equator to the pole, its climate changes. And that changes currents, and that changes winds, and that does all kinds of fun things. But it doesn't look like cosmic rays are very important. It doesn't look like space dust is very important. The sun's changes are blessedly small or slow, and if they're slow, the thermostat beats them. The history of climate looks more like greenhouse gases than anything else. And of those greenhouse gases, it looks like CO2 has been the biggest control on it. And this is an emerging picture that has come out in my career, but I think we were surprised. I think we expected other things to be more important. But what we see is CO2 mattering a lot, okay? And the big changes of the past, we could do something similar if we burn it all. Only we'll do it faster than basically everything except the meteorite that killed the dinosaurs. Right? So you will do this. You've probably met somebody. You may know somebody, right? People say, oh, climate's always changed, so we don't need to worry about changing the climate, right? I have had elected officials tell me that, right? The logic is fantastic, right? It is equivalent to nature has always caused fires, so we do not need to worry about arson. It is exactly the same logic, right? We have always died, so we don't need to worry about investigating murders, right? I'm sorry, this is sort of crazy. But when you look back, they drew those lines where things died. And we could do things that big, and we might do them faster. Fortunately, I scare students with this. And then I leave them with this one, which is that the big smile is that we're the first generation in history that can look at each other with a straight face and say, we know how to get off of this treadmill. We do know how to build an energy system that'll be sustainable. But the one we got isn't. So thank you for coming, and I'll let you go to more fun things than this.